We begin at the Salto Bayo Falls in Brazil, where this fella took the express elevator to the basement via kayak. Pedro Olivia rowed his boat a record 127 feet to the bottom of the falls and amazingly survived without a scratch. The drop took exactly 3 seconds. It breaks the old record by about 20 feet, and while it looks like they might have just chucked a dummy over the falls, like in the movie The Fugitive, the stuntman and his friend appeared on the Today Show this morning to verify the story. Mr. Olivier then kayaked off the Prometheus statue into the ice skating rink at Rockefeller Center. More stunt.
A joke, I think, but anyway. So this has, I guess, everything to do with what we've talked about so far in terms of Bernoulli's equation. I remember I was at Penn State then in, I think it was 1980, no, it's 1990, I'm pretty sure. Jesse Sharp, June the 5th, 1990. No pictures of it, but I'm sure you can find it. Also decided to kayak off Niagara Falls, but was never seen again. I think neither his body nor his kayak were ever found. Similar falls. I don't know whether you know this, but Niagara Falls, upstream of it, on both the Canadian and the US side, it's the border between Ontario and New York State, and they both sides have intake tunnels for hydropower. And so at nighttime, when no one's oohing and ahhing at the falls and looking at the light show that's on the falls, they actually generate electricity from it by diverting stuff instead of going over the falls, around the side through basically a hydroelectric plant. And so Jesse, unfortunately, was doing the same guy as this other guy in Brazil, I think. Niagara Falls is about the same height, I think, about 120 or so feet, they said, but has a bit more water in it. I think as he was going over the top, both the power plants on both sides of the river tried to divert water into their tunnels to be able to try and stop him, but they didn't do it fast enough, apparently. So, anyway, so that's all about Bernoulli. We'll also see this example in another circumstance. We'll use it when we talk about control volumes. And again, you can see that this is kind of Bernoulli in action. I'll try and freeze it where I want to freeze it. Maybe it'll evolve. So obviously it's filling up the glass with water in this case. But when we turn it on, if you look at this, it's an exposition of a couple of things in Bernoulli. One is that if we wanted to, we could write Bernoulli upstream and downstream. We could write the conditions that we know here, which we said last time we think would be equal to fluid pressure and elevation and velocity. We'll have to talk about the exam later. And we could do the same at this lower portion. If we knew 3 of the conditions here and only 2 of the conditions here, such as pressure and elevation, we could calculate velocity. And if we wanted to be able to deal with this, we could also apply this second requirement, which is in the background here. Oops, wrong one. Which is in the background here. Let me find the right location. I didn't quite do that right, did I? Whoops. And that is that we made the suggestion that when we use Bernoulli, what we can also do is we can apply this idea of conservation of mass, which is this term that we're dealing with here. And that is that the area times the velocity upstream and the area multiplied by the velocity downstream have to be equivalent to each other. And so I apologize for this, that we're going through this. I thought I'd set this up before, obviously I didn't. It's last time's. This requirement here. And you can see the exposition of that here by looking at the cross-sectional areas here. You know that by the velocity at the top has to be smaller at the top than it does at the bottom. It could be 0 in the limits at the top, but because it's accelerating by gravity, then it has to be faster at the bottom. And so if it's faster by the bottom, then the velocities have to vary according to the ratio of the cross-sectional areas. And so we can see that exposed in this picture here. And so that's what we'll talk about today, is we'll carry on dealing with Bernoulli, mainly along a streamline, and mainly applied to being able to define behaviors for a number of different examples, which we will attempt to look at. I'll go to this. Okay. So to recap, most of our action is going to be on looking at Bernoulli along a streamline. If it's inviscid, then these terms all disappear to zero. and we're left with 6 terms. We can solve it with either one unknown or 2 unknowns. If we want to solve by 2 unknowns, then we have to invoke this to be able to solve it. We can also do it normal to a streamline. Again, we have the same kinds of behavior in that if we look at this, it's not very well written for our uses, but in this we know that this is really an exposition of force equals mass times acceleration. This is the acceleration term. This is equal to force is equal to mass times angular centripetal acceleration. This is the acceleration term, and the other terms are those that relate to forces. And so they come from a common root, and really they are absolutely nothing different from looking at your dynamics class, your EMEC 212, that talks about motion of bodies governed by Newton's second law. We did an example last time that looked at free jets, so we have a standard solution for that, which is this. And I was just going to spend some time looking at this example that we've just talked about now. And the example we talked about now could be the falls. And we can make the falls easy for ourselves by having a streamline that goes across here. You might have noticed in that movie that the kayak, as it's going down, look at it again, and you'll see that the kayak's going down at basically the same velocity as the droplets of water that are going down. They're in synchronization. And so it's really just an exposition of this F equals ma. We could write the behavior of this between 2 locations, locations 1 and 2. We can make life easy for ourselves that instead of writing it here, where we would have some velocity that we'd have to include, we could use the big tank assumption and assume that the velocity is equal to 0 because the tank is large. And if that's the case, then we can write our expressions out as P1 pressure head over unit weight plus elevation plus velocity squared term over 2g is equal to the pressure at location 2 unit weight plus z2 plus v2 squared over 2g. And we could write this at 2 locations. We could write it where it's impacted the water at the bottom, at this point here, or we could write it at some location a small amount above that, and that would change the magnitude of our behavior. If we do it at the bottom where the velocity is 0, v2 is 0, then pressure will be equal to a large number because we've absorbed the energy and the change of momentum of the water has converted into a pressure. Or if we take it just above the point where it impacts before it stagnates, the velocity will be its maximum because it's accelerating downwards, and the pressure will be 0 because it's acting against it. So it depends on what we want to solve for. But regardless, we know that this is atmospheric. We know that in this particular example, this was equal to 120 feet. So this is what we call h relative to this datum. We know that if it's a big tank assumption, this is equal to 0. We know that if we choose our datum exactly where we've done it here, that z is equal to 0 at this point. And so we're left with the case of this value for this parameter here being equal to either one of these things. If it's above the impact location where the velocity is finite, then pressure is equal to 0. So this is, so in this case, this would be P is equal to 0. And in the lower case, V2 would be equal to 0. And depending on what we want to calculate from it, then we choose either of those conditions. So I suppose in this case, if we wanted to calculate what the velocity is before it impacts, like as in the free jet, then we choose this particular case. And we just get the fact that this would then be 0. And so h is equal to v squared over 2g, v2 squared over 2g, which is the same as saying the velocity is equal to 2g times the height, square root. So we would calculate the velocity of the water, same as the velocity of the kayaker at this particular location. And so we could do that quite straightforwardly. The other thing that we could do is that we could imagine some falls that look, instead of like the ones we have here, I'll draw them separately, instead of being vertically downwards and across, imagine that the falls are a slope that come down at some angle, and this angle is whatever, theta. We can do the same again. We can talk about a streamline. And we can do it between the big tank assumption, and we can choose a location. Let's choose the location, I guess I'll use it as red 2, right? Just to be consistent, before it impacts something. And so this is the case where the pressure is equal to 0. So if we go through the calculation again, nothing has changed. It's still this elevation here. We still have a velocity term. In this case, this will still be true. However, what's important to this, it seems to kind of violate our sensibilities that's the case. What you have to remember is that v is the streamline velocity. And so if that's the case, then I'm kind of running out of space here, but you can imagine this streamline velocity being this, v2. And there's a component of v2x, and there's a component of v2z. And they have to be the vector sum of each other. So if this is theta, then you can write out the fact that v2x is equal to v2 cosine theta, and v2z is equal to v2 times sine theta, just from trigonometry. And so if this is 45 degrees, this will just be square root 2, and so you can calculate this. And so you can calculate the streamline velocity directly from this, and it will be this, in the direction v2. But the components of it, you can look at the downwards component is actually going to be smaller. So v2z is going to be equal to v2 cosine theta. If this is 45 degrees, then this is 1 square root 2. And so I think cosine 40 degrees is just going to be equal to v2 1 over square root 2, which is about 0.7, right? 0.71, I think. And so it's smaller than the streamline velocity in this case, as you'd expect it to be, in the vertical direction, that is. And that's because it's coming down this rise, and it's only seeing the portion of gravity which is directed along its flow path. And so it's reduced in velocity from that. So it really isn't any different from being able to look at this. This is the velocity of the stream. It's going at 45 degrees. I don't know if it's the right direction. I guess it's the other direction for you as you look at this. And it has components in the x direction and in the z direction, and we can calculate those. And so that's useful for us to think about. And so that's why if we drop a kayaker from this point here, so that he or she goes down here, they're just moving at the same calculation that you can calculate that the location is equal to z is equal to velocity at location 0 times t plus a half AT squared. And you could make these calculations. And so if you wanted to, you could calculate, well, we can do it right here. If we know what the behavior is at this, you could calculate. So we could use this. Z is equal to V0 at time t0 multiplied by time plus a half AT squared. Z was 120 feet. 120 feet is 40 meters. The initial velocity at the top is 0 from what we said here. As you come over the lip, you'd expect it to be 0. And so in other words, if we rearrange this, we end up with 2 times 40 meters from this divided by acceleration, which is 10 meters per second squared. Square root is equal to t. 240s are 80 meters divided by 10. Square root is about 8. Square root 8 is about it's about 9, right? So square root 9 is about 3 meters a second. So we know that when it's hitting at about 3 seconds rather. Sorry. And if you remember in the dialogue or the narration that came with it, about 3 seconds to hit the bottom, exactly the same. And you could calculate that from looking at Bernoulli's expression as well. So make the point that we're really just dealing with bodies that happen to be in motion, and that we can think of them as individual particles of fluid, and they conform to F equals ma in all cases. Okay. So I plan to go through some examples just to make the points of how to solve these. And so there are 3 or 4 examples. One about fluids coming out of a tank, one about fluids hitting each other. We've already talked about, and one about gas coming out of a closed container, and one where we don't necessarily require that the top surface velocity is equal to 0. So I thought we'd just go through those and talk in general terms about how we might solve those. So the idea here is that you have a tank. It's made a bit more overly complicated than it needs to be. But you have a tank that's filled with water, and it has an outlet at the bottom that has a hose that's oriented in some direction at a magnitude of theta up from the horizontal. And the questions could be, or question is, how high is this arc that develops as it flies out of here? And it could also be, for instance, how long is it that this arc is as it goes from this location to where it comes down? And so how might we do that? We know that we can write our conditions at a couple of locations. And so if we want to look at a streamline going through this green line, which now is a red line, comes through here. So we could write the behavior at this point. Okay. Before we do that, let's back off. What happens if we had a hole in this tank here and a tube coming up to this level here? If the tube came up this high, if it's open here. Well, we know from fluid statics that presumably the water elevation in this tube should rise to this point here. If we make the tube shorter than that, whoops, oh, I guess I have to draw it in completely. If we make the tube shorter than that, then we can do the same, but we can do it with Bernoulli. And we could write it in terms of, I guess we have points 1, 2, let's call this point 4. If we wrote Bernoulli in terms of this, P4 over, well, let's not do that. We've said always that we want to do it as a system upstream to downstream. So upstream to downstream would be this. So it would be P1 over unit weight plus Z1 plus V1 squared over 2G. And that has to be equal to the behavior here, which is the pressure at point 4, the elevation at point 4, and the velocity at point 4. Top of the tank, pressure 0. Elevation of the top of the tank, if we take this as 0 here, then this would be h, uppercase H. The velocity at the top of the tank, big tank assumption, this is 0. Pressure at point 4, it's emanating into the atmosphere. All the arguments that we had last time, that horizontal pressure has to be 0, so the pressure at this point has to be 0 also, if we're taking atmospheric pressure as 0. The elevation of this point, well, this point here is equal to z by definition. If z equals 0 is our datum here, then plus z is this point here. And this is what we don't know. And so what we can do is we can just rearrange this. The only terms we have are h minus z is equal to v4 squared over 2g. And so if we rearrange that, we end up with velocity is equal to 2g height minus the height of the tank minus the elevation of the point, square root. So it's just a modification, if you like, of our equation for a free jet. In the same way that we did the example with flow going down this inclined plane, it's a streamline velocity we get. It doesn't matter if we're looking downwards or if it's deflected upwards, it's the direction in the streamline. And so in this particular case, the velocity along the streamline you'd expect would be vertically upwards. If you move this tube up to this point here as we did before, then the heads are equal to, these are equal to each other, and the velocity should be 0. Kind of makes sense from what we said. But if we don't have this tube come up here and it squirts up to this point, just like the syringe example, then it should be at its top of its arc here, and the value of the velocity is also 0. And so when you think about this squirting out, really what we're doing is we're just exchanging energy in different forms. Here we have potential energy. As we come down here, it comes through this. It has kinetic energy as it comes up here, and it trades that kinetic energy as it goes up to this point, again for potential energy as it's at its highest location. So we're just swapping between these forms of energy. This is kinetic energy, this is potential, and this is fluid pressure or strain energy within the system. And we're just trading between those different components. All right, so that's how we can rationalize exactly what's going on here. How do we figure out exactly what is happening at this point? So what we can do is we can first of all solve this problem by turning to write this equation between 2 points 1 and 2. And that's exactly what you have here. We've already said what some of those values are. This is 0. This is 0. And this has to be uppercase H, height. So we have the left-hand side because we've done that already. What are the conditions that we have here? Pressure at point 2. It has to be atmospheric just outside here because fluid atmospheric pressure is acting on its side. So pressure 2 has to be 0. The velocity is probably not 0 because we've exchanged energy from this potential energy to kinetic energy here. So this is not 0. But we do know what the elevation of this is. The elevation, not very easily, is equal to z2, which is equal to L sine theta. I guess uppercase L sine theta. So we know this. This is equal to L sine theta. So we have everything in here that we know, but we don't know the velocity. We know the velocity is a streamline velocity. If the velocity is a streamline velocity, this is v2. It has 2 components. We could figure out in solving this in 2 particular ways. The first way is to think about the other Newton's law, equal and opposite reaction is one of them, but the other one, a body in motion stays in motion unless acted on by some other force. So that means if this ball is moving towards the wall at 1 meter a second, if there are no forces applied to it, it will keep on moving in that velocity. If I throw it through an arc and it goes up, the horizontal velocity will always be whatever its initial horizontal velocity is. And so what we could do is from V2, we could calculate V2x, because we know that V2x is going to be equal to V2 cosine theta. And that is the magnitude of the horizontal velocity coming out of here. If what we've said is that it doesn't slow down as it goes horizontally, what's going to be the velocity in the streamline at point 3? By definition, the velocity coming out of here is this V2x. It's going to be exactly the same velocity here. So V3 has to equal that. And so since we know what V2x is out of this, we certainly know what V2 is from this expression here. This is our only unknown. If we know what the angle theta is, then we certainly know what V2x is. And if we know what V2x is, we know what V3 is. If we know what V3 is, then we can write Bernoulli equation in terms of the behavior here or the behavior here. It doesn't really matter. It could be P1 over gamma plus Z1 plus V1 squared over 2G. It's probably easier to write at this point, is equal to P3 plus Z3 plus V3 squared over 2G. We know this is 0. We know this is uppercase H. We know this is 0. Everything on the left-hand side. We know that the pressure at this point, for all our arguments before, acting across this jet, has to be 0 also. We know that V3 squared has to equal this. And we know this. And so we know this term. And so the only parameter that we don't know is that. So it's kind of a complicated example because of this angle and the length L. It's much easier. It's actually turned up on an exam just as a jet coming out of the bottom here without this length, where it's much easier to solve. But basically we can get the value for Z3 from looking at that. And so you just have to realize the fact that horizontally we can, and that's the reason for showing this example of the falls, Niagara Falls, and the slope, is that this velocity here has to be the same velocity here. The other thing you could do, you can see there's another way to do it, and I won't go through it in great detail, but the other way to do it is that you also realize that there's a velocity here coming out, and this would be V2z. And you can calculate, it's just going to be the sine of this. So V2z is equal to V2 sine theta, I think, right? Acting upwards. And so the idea of this is, it starts off with some velocity coming out of my hand, and it arcs up to some location where it doesn't have any velocity anymore. And so you could write something between 2 points where the velocity, the vertical velocity at this point has to be what? By definition. It's horizontal. It only has a horizontal component of velocity, so the vertical velocity at this point has to be 0. So you could write, just by solving the equation for throwing this ball up in the air at some acceleration, or some initial velocity. So you could use this expression we already defined. What was it? The height traveled is equal to velocity times time plus a half a t squared. I guess you'd need to know something about the time it took to go up there. This initial, actually you can't use that, can you? You could write Bernoulli's equation for a free jet. The easiest way to write it would be just that velocity is equal to 2gc square root. This is the vertical velocity in the z direction. This is gravity. This is the velocity it comes out at in the vertical direction. You'd find out that this elevation here would be the height above this point that it gets to before it stalls out. Basically the equation of a free jet. Okay, yep.
So whenever you solve Bernoulli for the at point 2, the V2 that you get, is that going to be in the x direction or the z direction, or is it out at all?
The V2 you get from Bernoulli is the streamline velocity. So it is always going to be in this trajectory here. It'll be yeah, make it a dog's breakfast out of that. But it'll be tangential to this arc, aligned, yeah, streamline. It's always a streamline velocity that we're dealing with. Okay. So made a bit more complicated by the fact that we have this tube coming out of it, but nonetheless, the key points are to be able to resolve directions. Yes.
Why did you say the pressure in the tube pointing to zero?
Because it's coming out into the atmosphere, and whoops, I didn't mean, I'm just going to draw something. And so the idea is that it's coming out of this. So the question is, why is the pressure zero, right? So you have a tube that looks like this. And so clearly within here, the pressure is probably not zero because it's confined. But when it comes out as a jet into the air, then at this point here in the air has to be atmospheric pressure. Atmospheric pressure has to act in the same direction in all directions. So this is P equals atmospheric. And so if it's acting atmospheric pressure in this direction, and it's also acting at atmospheric pressure in this direction, then for this to be continuous, if you do a free body diagram of a little packet of fluid, what's the pressure that has to be acting on a weightless fluid that's acting in this direction? It has to be zero. And so if the pressure in the center of this jet also has to be zero because it's acting against this sideways zero pressure, then it also has to be pressure zero in all directions. So that's the rationale. And so it matters where you take this, because at this point it would not be equal to zero. And so I think germane to this talk or discussion is this idea here, and that is that it really matters where you choose to take it. We can take it before it impacts the pool at the bottom of the falls, in which case the pressure would be zero and the velocity would be non-zero. Or we can look at the stagnation point where the velocity is zero, and therefore the pressure probably is not zero. Because it's basically, imagine getting hit in the chest with a fire hose. Before it hits you in the chest, it really has zero pressure acting on it because the fluid pressure acting in the atmosphere is zero on the side. But when you destroy the momentum of that, you feel it. So it's the destruction of momentum that we're feeling. All right. Second question. We'll go through. So, two tanks. One tank, which is pressurized, has fluid squirting out of it, hits a jet that's coming from a second tank. They meet. The two jets, like two cars colliding. When two cars collide at 30 miles an hour, if they're the same mass, they stop dead, right? Because they exchange momentum completely. And so that's exactly what's happening here. There's a streamline that's coming out of this jet here, which is ending up at point A. And there's a separate streamline which is coming from point 2 and ending up at A. There is not a streamline that comes out of 1 and ends up at 2, because it's not a streamline, right? One is coming down here and squirting sideways, and the other one is going up here and squirting sideways. So they're two separate systems. So you cannot write Bernoulli's equation between 1 and 2. But you can write it between points 1 and A. So P gamma P1 plus Z1 plus V1 squared over 2G is equal to PA over unit weight plus ZA plus VA squared over 2G. And I'll just write Bernoulli for the other condition as well, together. And so maybe we'll write them in the same location. And that is P2 on this side. And it has to equal the behavior at point A as well. So this second part is identical to the material right above it. So what do we know? Pressure, point A, we don't know. It's impacting, and so we don't know exactly what that is. We're going to take it right where the ball has hit my chest, and it's transferred its momentum to my body. So the velocity at A, in both cases, they're both stagnation points. It's hitting here. The streamline velocity in the direction of the streamline is 0. It has to squirt horizontally, but it's orthogonal to it. So at the point where it impacts, it's 0. The location of A, I guess we know that this is 20 feet. So we know that. And we don't know what this is. Not a very good question mark. So we don't know what that is. What do we know about the other conditions that we have? So we know that we have at least one unknown on the right-hand side that we don't know. What do we know about the other systems? Take the first one. We know that the air pressure here is 25 psi. I'm not going to do the math on this, but I can write in the magnitude. Big tank approximation. What's the velocity of fluid within here? And we know the elevation is 8 feet. So we know everything on the left-hand side, and we only don't know one thing on the right-hand side. So we can solve for this, because we know all those dimensions. What do we know from jet 2? Well, we want to know exactly what this height is. So if we've taken the datum as 0 at this point here, and implicitly we've done that because we've called this 20. So the elevation of this second point is going to be 20 plus h. Which we don't know. Pressure at point 2. Atmospheric. So 0. And again, the big tank approximation is this. So here now we only have one unknown, which is this, and it happens to be equal to the same amount above. So we have two equations, we can equate them to each other, and we can solve. We actually have two unknowns in this equation, right? But we know what PA over gamma is exactly from the previous equation, because it's our only unknown. Substitute in here, and then we have everything to calculate what h is equal to. That's it.
Would you have to make one of the 20s from the A side equal to -20?
One of the 20s on the where? This one?
Yeah.
No, you should use it always relative to datum. So if this is equal to z, then this is equal to plus 8 in terms of z. This is equal to plus 20 in terms of z. And this is equal to plus 20 plus h, which is this. Does that answer your question? Always, yeah, always choose a datum. Always our z is vertically upwards, positive upwards. And it doesn't matter where we took the datum. If we chose our datum to be z equals 0 here, then this would just be minus h. This would be minus h plus 20. And this would be minus h minus 20 plus 8. So just do your accounting. Right? Yeah, and there's some comments in there as well. We've talked about this. We talked about the fact that if we use Bernoulli's equation, sometimes we only have 4 known variables out of the 6, and we need to make some assumptions to be able to close the system. And the easiest way to do it is to write that the cross-sectional area of flow upstream and the velocity are equal to the cross-sectional area of flow and the velocity downstream. It's not quite true. I guess we should also multiply this by the density upstream and by the density downstream. Usually the densities are the same, but what we conserve really is not flow volumes, but we conserve flow masses, mass rates and flows. And so we didn't do this last time, but strictly speaking, when we talk in weeks 6, 7, and 8 about conservation equations, we'll always work on conservation of mass, conservation of momentum, and conservation of energy. Conservation of momentum, well, conservation of mass requires this requirement. Maybe a bit more of a detail for now, but one that we perhaps can mention. We've taken a kind of an easy route in most of the calculations we've done, in that we've always made this big assumption of the big reservoir. And that doesn't always have to be the case. And if that's not the case, then we do need to typically invoke something like this expression that's written above here. And that is that the mass flow rates are equal upstream and downstream. If it's a compressible fluid, then usually rho 1 and rho 2 are the same, and really it just does become A1 V1 equals A2 V2. So that's usually the case, but not always. And so one exposition of this is this example. So instead of assuming the big tank relationship, where the value of the velocity here is 0 because of big tank, and therefore the velocity, the tank level is not dropping as a function of time as we pour stuff out the bottom. If you imagine shrinking this tank diameter smaller and smaller, then that becomes a more and more difficult requirement to adjust for. We know that Bernoulli has to be steady state, so the only way we can keep this as steady state so it looks the same at time 0 as it does at 10 seconds and 100 seconds is that we have to keep on filling it up with water by a spigot to be able to keep it at this elevation. But we can solve this problem merely by allowing the fact that the velocity at 1 doesn't necessarily have to be equal to 0. And so what we can do, and I'll just walk through this, I won't maybe go through it in complete detail, is that we can write Bernoulli's expression written slightly differently from our form here, but you see it's basically the same expression that we're dealing with. The upstream conditions are what? We're on the surface, so by definition the pressure here has to be 0. It's a steady state problem, so the elevation of that water surface has to be 0. So it has to be equal to h rather, which is c1. And we're not going to constrain it by making sure that the velocity 1 is equal to 0. We're going to allow it to be non-zero. And that's allowed by the fact that we're pouring fluid in here. So by definition, if we're pouring fluid in here, and if we smear this fluid across the whole width of the tank, then the tank velocity has to be non-zero, right? It's given by whatever the rate in here is. We can write the downstream velocity behavior in terms of the fluid pressure it comes out at, which is 0 for the arguments that we've made already. We know the elevation, if we take the datum here as being z equals 0, then this is also equal to 0. And the velocity we don't know. And so what we do know is that we know the conditions, 4 of the 6 conditions, which are the ones that are circled, but the ones that we don't know are going to be these. And so if you look at the equation below, you see that's all substituted. The things we don't know in Bernoulli's equation are these 2 unknowns, but we can equate them. We can write that the fact that the cross-sectional area at location 1, which would be this area here, times the velocity 1 has to be equal to A2 V2. We can change that to be the fact that velocity 1 is equal to A2 divided the ratio of the areas. And if we know the diameters, we know that A1 is equal to pi d squared upon 4, and A2 is equal to pi lowercase d squared upon 4. And so this is just the same as the ratios. The pi's and the 4's cancel out, so this is just lowercase d squared over uppercase d squared times V2. Which is this bottom equation here. And so the utility of that is that we can square this, which squares this, which makes this this. And we can take this expression here and we can pop it in there. So now instead of having one equation with two unknowns, we have one equation with only one unknown, which is V2, and we can solve it. And so we've just used continuity to do that. And if we make that substitution and do the math, then we end up with this bottom equation, which says that, if we want to write it out, that velocity at point 2 is equal to 2gh square root multiplied by 1 over 1 minus d over d to the 4th, also square root. So this just says that there's the equation of a free jet, which is this first part, which is the velocity that we'd expect it to come out of if we assume that the velocity on the top surface of this container is equal to 0. And that's what this term is here. But if we allow for the fact that this velocity is able to go down at some velocity v1, which we can calculate, then as a result of that, then there's a correction factor, which means that the flow rate is always going to be reduced, right? This is always, this could be, if the tank is really huge, then big uppercase D is very large, and this term on the bottom is just equal to 1. Square root 1 over 1 is 1, and there's no change. As the magnitude of this D becomes close to this, it becomes undefined, right? Because it's 1 minus 1, which is 0, square root infinity is not a very useful number. And so it becomes, or square root, 1 over infinity is, it becomes a much smaller, which way does it go? So when it's, certainly when it's equal to a large tank, there's no effect. When it's equal to a small tank, then it reduces it, and it doesn't make any sense when it's less than 1, right? Because the diameter of the tank is less than the pipe. So I guess in this case, D has to be slightly larger than lowercase d. And so if we wanted to be able to look at the ratios of the flow rates between the free jet behavior and the behavior when we have the non-zero velocity, actually the other way around. This is the one on the bottom, which is the free jet, and the effect when it's non-free jet, we can plot those results, and we get this result here, which says that the magnitude of this is equal to 1, which is, there's no effect of this velocity at the surface, except when there's about a 5% effect when the diameter of the tank is less than maybe twice the diameter of the outlet pipe. If it's less than that, then there's less than 5% difference, and hence our justification for using this large reservoir volume expression, which allows us to basically take velocity 1 is equal to 0. Okay. We won't get to the final one, don't need to, we'll talk about it later on as a decapitated gas cylinder. That's it for today.